Welcome to 25th lecture of video course on tribology. So, we are going to complete today quarter century of the lectures on tribology. The topic name is estimating elastic deformation. It was started long time back. It is started more like a mechanical element. When they come in a contact, there will be elastic deformation and plastic deformation. We are restricting our discussion to elastic deformation. We don't want plastic deformation, we don't want permanent deformation on the surface. It should recover back once the load is removed or after unloading. In previous lecture, we started with hydrodynamic lubrication and explored how to model hydrodynamic lubrication between the tribal pairs. And in present lecture, we are going to combine elastic deformation with hydrodynamic action. That's why the topic name maybe also can be termed or can be called as elastro-hydrodynamic lubrication. Here we are going to mix elastic deformation of the materials, hydrodynamic action due to velocity, and lubrication because of the presence of lubricants. A couple of the few slides which we discussed in previous lecture, and I'm just going to repeat for the continuity. Say that this figure is showing the two spheres, they are in contact, and of course the circles are shown as a front view of those two spheres in a contact. It appears initially that there is a point contact, but if you apply the load F, point contact cannot be sustained. There will be infinite stresses, and we know there will not be infinite stresses, there will be some sort of deformation. Material will deform to sustain the load, and that deformation to a bigger scale is shown over here. Of course, this deformation will be very, very low. That is why we can say the half width, if I say the 2b is the total deformation which is shown over here, or we say this is the B and there is a symmetry in both the sides. This B must be very, very low compared to D1. Now, we say B need to be lesser than D1. It may be even lesser than 1%. It does not reach even the 1%. Just to sketch it so that we can demonstrate pressure distribution, we have kept in a bigger scale. Or we say that these figures are not on a scale, it is just a demonstration, is a schematic diagram. And when this kind of deformation occurs, you can see there will be contact area, and that contact area in this case particularly sphere versus sphere will be a circular. R2, if there is some sort of misalignment, it may be elliptical, but in this mostly there is a circular, and we are assuming that this radius starts from 0 to max value of B, where the maximum deformation occurs. And experimental reports indicate that pressure will be parabolic. Maximum value will be at the center, or where the load is coming, the maximum pressure will occur there, and it will gradually decrease, or maybe say parabolically decrease, not gradually, is it parabolically decrease to the 0 value, and an extreme boundary B, or when R is equal to B, this pressure will be 0. Now, what is our interest? To find out how much elastic deformation really has happened, or what is this contact area. Now, there are two variables. We say that it is radially compressed as well as the flattened also. So, we have two, but this is the D is a deformation and B is a width of the contact, or we say that this is a circular area, R will be variable as well as this deflection will be variable. For convenience, we start with parabolic distribution. We say the pressure at any radius will be equal to P maximum, that which will occur at the center with R is equal to 0, and the square root of 1 minus R by B square. R is going to vary from 0 to B. When R is 0, pressure is going to be maximum. When R is equal to B, that means B by B will equal to 1, 1 minus 1 will be equal to 0, that means pressure is equal to 0, and this is what we are showing through this diagram. Pressure will be 0 at the boundaries and maximum at the center. That means this kind of relation is representing pressure distribution which is generally observed in experimental results. Now, as as a common thing given to us is a force, how much force is applied on the materials. Of course, with the elastic properties, like in this cylinder we have Young's modulus and knew that Poisson ratio as well as geometry radius. So, these two elastic properties, this is a geometric property, the material property, geometric property, we need to account this. And force is generally given to us. Naturally, all the parameters like related to B or deformation can be figured out once we find out the expression for the F. So, we say that the total load on can be represented as integration of P or the P into dA and integrate over the complete area. And what is the complete area? We say this is circular. So, at any point if we starting 0, theta is equal to 0, it will complete at as a theta is equal to 2 pi. That is why it says that first integration limit for theta is 0 to 2 pi, and second is a radius 1, and this radius is going to vary from 0 to maximum value of the B. This assumption the maximum patch, the width is B or radius maximum value of the radius maximum value of R is equal to B. So, that is why this says integration from 0 to B. Now, P we are assuming that it is equal to the P max square root of 1 minus R by B square. We can substitute over here and we can integrate over there. However, we can see that there is a no theta in this P. That means P r dr can be kept separately, and this first integration can come out as a d theta, and integration will be theta, and we can substitute value of the theta, that is a 2 pi minus 0, it will turn out to be 2 pi, and that is shown over here. The force F is equal to 2 pi. We have already integrated over theta, substitute the values of the boundary 0 and 2 pi, that means 2 pi minus 0 equal to 2 pi, that is the 2 pi over here, P max. Now, we can rearrange P max is also does not depend on R now, we can take it out and we can rearrange. In addition, we have rearranged this bracket also. We are saying that now is a B square minus R square. We are taking 1 by B as a common from this, which is also constant for given force, given geometry, given elastic limits, B will remain constant. So, this bracket remains, which is need to be integrated, that is a B square minus R square, and limits are 0 to B. We know this is simple integration. We can substitute B square minus R square is equal to some variable, differentiate it and substitute this value. For time being, we are assuming that B square minus R square is a T square. If we differentiate, it will turn out to be minus 2 R dr, which is here R dr, we have to substitute, and this side will turn out to be 2 T dt. That means, we can substitute easily, this is T and R dr is given as a minus T dt. Now, this integration is pretty simple. So, T square integrating, it will turn out to be T cube divided by 3, and we can substitute the values of this dt. The integration limit has been changed. Here integration limit was 0 to B, but this is a negative side. So, that is why the integration limit is turning out to be different, B and 0. Or let us say that when B is equal R is equal to B square, T will turn out to be 0, that is been shown over here, and when B is equal to 0, T can turn out to be plus minus B. We are neglecting the term minus B because there is no negative geometry in this, it has to be only B, cannot be negative B. That is why we are writing something like that, 0 to B integration. Now, as I mentioned, that T square integration is simple, T cube by 3, that is shown over here, T cube by 3, and we are substituting the values. So, B instead of T turn out to be B. So, it is showing the results as B cube by 3. Of course, the negative sign will change because of this limit, it will turn out to be 0 minus B cube by 3, and negative will cancel out or will turn out to be positive. That is why the overall expression turns out to be this. However, there is a common one term, that is a B here and B cube here. We can simplify and we can express this relation something like this. So, F, the applied force, is equal to 2 by 3 and 66% into pi, that is constant, B square P max. Now, many times we know that what is a P max, what will be maximum compressive force which can be applied on the on this kind of elastic body, or at which stress or which pressure it will start deforming. We can substitute those values. However, if we do not know this value then we need to use some other equation also. I always say that we know force, but there are two variables B and P max. If I use elastic properties of material, you know, I know the P max, what will be value of P max, I can simply find out what will be the B. If I do not know with a surety what will be P max, then I had to use some other relation. I had to try with using some other relation. However, in this case we have discussed about the spherical contact. The second general contact is a cylindrical contact, that is shown on this slide. They say that in the cylinder, why we are saying the cylinder, because in this case the length is much larger, maybe more than 4 times of the diameter, and the radius is given as R1 and R2. Both the cylinder have the same length. It is a typical example of the roller bearing. In roller bearing, many times we keep L by D is a 1, but in this case we are assuming that is much larger, that maybe L is more than 4 times compared to the diameter. And pressure distribution, because there are two rectangular component, x component and y component, we can give pressure distribution something like this. Again, the P will be maximum at the center, and x as a direction shows here x, as x varies, it will vary, and when it reaches to maximum value of the contact patch, that is equal to B, pressure it will not be 1 minus 1 equals 0, whatever the value remaining here, that will can be shown or can be represented. However, as our assumption, this length is much larger. The pressure distribution or pressure variation along the y axis may not be very dominant. So, we may neglect this for the time being. You can say that y by a square term is negligible compared to 1 compared to x minus x divided by b square. If we neglect this, and pressure term will turn out to be much simpler, the way which we have solved in the previous slide. Same thing. In previous slide we use the word letter R instead of x. In this case we are taking only the rectilinear coordinate system. In previous slide we considered polar coordinate system. Now, the P is known to us, we can substitute in the force equation and integrate that force equation to find out what will be the relation between the F, B and P max. So, when we do that, this F here, dy, the way we have done earlier, the d theta, the same thing, and the dy will be simply integrated, it turn out to be L, and here it is 0 to B, P max 1 minus x by b square dx. Now, P max is also constant, it can be taken out easily, and then we can substitute something x is equal to b sin theta, b cos theta and some other term, and get the integration done. For time being, in this case we are substituting x is equal to b sin theta. Okay. So, when you substitute x is here, b x x is again substitute b divided by sin theta, sorry, b is sin theta divided by b, b will cancel out, it will now turn out to be 1 minus sin square theta. When you find out, it will turn out to be cos theta only. When integrate, dx is equal to, it will turn out to be b cos theta. So, overall this term turn out to be the cos square theta. We know integration of cos theta square, cos square theta is simpler one. It can be termed as a cos 2 theta plus 1 divided by 2, and we can integrate because we have integration limit given over here. So, when we integrate cos 2 theta and integration limits are 0 and pi by 2, the overall integration will turn out to be 0, because sin 2 theta, we substitute pi by 2, substitute 0, both the values will be 0. However, plus 1, whatever which will come out to be the cos 2 theta plus 1, that plus 1 can be integrated easily, that will turn out to be theta, and when you substitute these boundary conditions or this integration limit, it will turn out to be pi by 2. We can substitute those values, and this overall expression turn out to be in terms of pi, b, l, p max. Now, again the way we can we have treated spherical contact, we can similarly quote the same thing about cylindrical contact. We say that if we know the p max, I can find out what will be the b value. L is already known geometry, this is a constant. P max, if I know the material, I can simply find out what will be the contact patch width when we apply load F for some materials. Now, we can compare these two. We say the spherical contact with the cylindrical contact. You can see there is a 2 by 3, here it is a 1/2. So, the 66%, this will be 50%. Pi is a common, while one B is common, but second B, there is a B, while here it is L. Length is generally very large compared to B, maybe order more than 10 times. And P max, if the material is the same, the P max will remain same. So, what is the conclusion coming out from this comparison? We can say that as a B is much lesser compared to L, and this difference is not very high. This is 66%, this is a 50%. This difference is not very high, there is only 16% difference, but B will be 10 times. So, we say that more than 10 times, the 6.6, while this, sorry, in this case the B will be 1 time, that L will be 10 times. So, I can say that this is a 0.66 and this will turn out to be 5. So, 5 versus 0.66. In other words, that cylindrical contact can bear much larger load compared to spherical contact. So, whenever there is a larger load limit, or we need to carry, or which other tribopia need to carry larger load, we should switch from spherical contact to the cylindrical contact. We know very well the friction force will increase with a spherical contact, cylindrical contact. In a spherical contact, friction force or friction resistance will be lesser compared to cylindrical contact, but load carrying capacity is higher. So, which is the advantage? If we have a space restriction, we know that more dimensions are permitted along the length direction, but lesser dimension is permitted along the diametral direction, then we can choose a cylindrical contact. Of course, we will discuss these things when we discuss about the roller bearing or selection of the rolling element bearings. The question comes, maybe I do not know the P max and I do not know B, how to find out this B when we do not know the P max. So, we can start with some strength of material equation. We say that assume this is a spherical contact, and under deformation, this delta 1 is a deformation. When we are applying the force, there is a deformation over here. This can be represented with the applied force, geometry or material parameter, and geometry. What is the radius? If I keep equal to B, I should be able to find out what will be the relation. However, if I do not know F as it is, and if I know the pressure distribution the way we have done earlier in previous example, pressure in terms of pressure, we can find out in that term. Now, why we are emphasizing on the pressure? Because when we discuss about the hydrodynamic lubrication, we have not discussed in terms of force, we have discussed in terms of pressure distribution. So, we will be knowing what will be pressure distribution after solving the hydrodynamic equation. However, if we do not require hydrodynamic, we require simple elastic deformation, then we can treat directly F. We do not have to come to the pressure. Well, we require elastic deformation to be combined, to be joined with hydrodynamic lubrication. That is why we are talking about the pressure term. We are giving explanation in terms of the pressure. So, when you do that, represent F in terms of the P max the pressure distribution and area dr theta dr. So, this overall can be represented in terms of B now, because we require relation also in deflection and extent of the zone or extent of the contact zone. And this is what the same distribution is being shown as the coordinate system, and this is formula available in a number of textbooks. One reference is been given over here. Now, when we substitute this rearrange equation, what we get in integration bracket is 1 minus r by b square root of that dr. We can substitute r as a b sin theta, simple, to get the value of integration. When we substitute here and rearrange, we are getting this term in this form of the cos 2 theta plus 1. We have done earlier, but here I have written in more explicit form. Now, when you integrate cos 2 theta, it turns out to be sin 2 theta, and when you put this limit 0 and pi by 2, both the terms will be turned out to be 0, and this is only important to integrate. When you integrate 1 into d theta is when you integrate, it will turn out to be theta, and you substitute this value, it will turn out to be pi by 2 minus 0. So, we can substitute these values and integrate the way it has been shown here, sin 2 theta divided by 2 plus theta. This is turning out to be 0, and this will turn out to be pi by 2 when you substitute this integration limits. So, now what we have? We have this deflection in terms of B, in terms of P max, and we can use a previous relation what we have done for the spherical contact, that is a 2 by 3 by B square P max. Now, we have also P max and B here. We can use this relation and we can find out the in terms of B relation. However, there is another possibility. We can go ahead with some sort of simplification. We can use a Taylor series to find out exclusively what will be the B in terms of F, neglecting or not neglecting and replacing P max with other geometric parameters. To do that, we can simplify it. We can say first I am substituting value of the P max here. I want to replace P max with F and represent this deflection or radial deflection on the surface, that is turning out to be radial deflection in delta 1 as 3 by 8 divided by B. So, these are related 1 minus nu square by E 1 F. Now, we are considering only the deflection of the one surface. We cannot consider deflection of both the surfaces. There is a possibility the other surface is rigid enough, it does not deflect at all, or if there is a deflection, then we should consider delta 2 also, and this will be changed 1 minus nu square divided by E 1. All other things will remain same because the contact patch will remain same. B will remain same for both the material. It is nothing like the one material will have one B1, another material will have a different B. We are coming in a contact, they are making a pair, so they will be having same value of B. Now, what do I say the simplification? That simplification can come from the geometry. We know very well that this deflection will need to be much lesser than the radius of the sphere. That is why I say that OA is a radius, OB is a radius, and when we are deflecting it to some extent, it is after deflection this sphere is getting shape of OC, or there is a deflection this much inside. Now, that can be represented in terms of OB minus OC. This is OB minus OC, that is a deflection. We know OB is radius R1, while OC can be represented with this triangle, right angle triangle, that is OA square minus AC square. OA already we know that is R1, and this is in terms of B, that half width or we consider the overall deformation or the extent of the contact zone as a 2B. So, this will turn out to be B. So, this is R1 minus B square, and we know B need to be much lesser than R1. So, we can rearrange, we are taking R1 common from this and overall common from the brackets, it turn out to be 1 minus square root of 1 minus B by R1 square. Now, we can use a Taylor series for this. It will be 1 minus half B by R1 square plus higher order term, as a B is much lesser than R1. So, this term higher order term will be negligible, that is why we are writing here somewhere the negligible terms. Now, the delta 1 can be represented here in terms of R, and in bracket is a 1 minus 1, and this minus 1 and minus 1 will turn out to plus 1, plus, and this is what will be in the R1 divided by 2 into B square divided by R1 square. So, this is the same thing what we have mentioned, R1 B square divided by 2 R1 square. Now, there is one relation over here in terms of delta and B, there is another relation delta and B here, and we know the force is given to us, elastic properties of material will be known to us, geometry of the contacting surfaces will be known, or generating body will be known to us. So, if we can simply find out what is the deflection in terms of the force, or what will be the contact patch in terms of the force, that is very clear from this relation. I can find out either delta or B, it will not be much problem. There are two equations, two variables, both will give a straightforward relation to us. So, here the B power cube is given as a 0.75 R1, this is elastic properties into F, or another word what we say that as the F increases, B is not going to increase in the same order. I mean, if you make force 8 times, then only the B will increase by 2 times. So, sensitivity of the deformation is much lesser in this case. obviously with a slight deformation, load carrying capacity of this material will be very high. At least B need to be lesser than R1 and much lesser than R1. If that any time that kind of relation is violated, then we will not be able to get the results properly. That is why we say in B need to be much lesser than R1, that you make sure whenever there is a deformation and we need to compare, if any time the B is turning out to be more than 1% or 2% of R1, we should stop, we should go ahead with the nonlinear analysis. This kind of a simplification will not valid. Now, the question comes, how do we incorporate in hydrodynamic lubrication? We have talked about only the solid mechanics in this case. We talk about the deformation in terms of the force, but how to combine with our hydrodynamic lubrication, which we have discussed in previous lectures, and we have more interest in that. When we can combine hydrodynamic lubrication with elastic deformation, then only the name can be given as elasto-hydrodynamic lubrication, which is important, as I say, that is one of the optimum tribopair mechanism. If we are able to achieve elasto-hydrodynamic lubrication throughout the life of the component, we cannot achieve better than that results. Hydrodynamic lubrication is not as good as elasto-hydrodynamic lubrication. Mixed lubrication is not as good as elasto-hydrodynamic lubrication. It is only the elasto-hydrodynamic lubrication which gives the best results. And most of the high performance tribopairs are designed based on elasto-hydrodynamic lubrication. Talk of the gears, talk of the rolling element bearings, talk about the cam and follower mechanisms. They have been designed based on elasto-hydrodynamic lubrication mechanism, where the load carrying capacity is enormous. With a much lesser area, they are able to sustain much larger load. Now, so question need to be answered, how to incorporate deflection in FDM or finite difference method, which was used for hydrodynamic lubrication. We derived deformation in we derived in FDM pressure distribution or found nodal pressure. What we did in finite difference method, we developed the surface, divide the surface in number of division, we say there are number of nodes, and those number of nodes we found pressure distribution. Now, if I know the pressure distribution of those nodes, I can integrate those pressure to find out the force. If I know the force of the different nodes, I can find out what will be the deformation because of those. However, there is a surface connectivity, whole solid surface need to be integrated. It is nothing like that they are individual molecules, individual pieces, and they will simply deform under the load. Here we need to incorporate a combined load, and that is comes what we are trying to convey. This is a deformation which we have done in earlier case in a previous slide in polar coordinate. Here we are writing in rectangular coordinates, because the pressure what we have expressed in hydrodynamic lubrication, it was in terms of x and z. And so, there is a area dx into dz, and this is the main thing. I will say that this is the distance. What is the distance between the pressure and the deflection point, where the pressure is applied and where we are calculating the deflection. Now, we cannot calculate the deflection on the same point where the pressure has been applied, because that will simply penetrate, will give the infinite stress. That is why we consider the moment equation, we take some distance from the pressure point and evaluate the deflection. We do not calculate the deflection of the same point. Now, more and more accurate can be achieved when we go ahead with a more and more number of divisions. This is what we trying to convey. See, now the pressure, suppose P I is somewhere here. I want to calculate what will be the effect of this pressure over these nodes, this node, this node, this node, this node. And keep in mind, pressure at any point is going to influence the deflection of the surface, because the whole surface is connected. It is a solid surface, they are not separated. Think about the diaphragm. When we apply a pressure at any point of the diaphragm, whole diaphragm gets deflected. It is not only that point gets deflected, the whole diaphragm gets deflected, and we are going to take those consideration, so that we get overall good results. Now, just for the example I have given in this case, if I want to find out the deflection at the fifth node in x direction and third node in z direction, what we are saying, if this is a 1 1 starting, is a 1 1 1 2 sorry 2 1 3 1 4 1 5 1 5 2 5 3. That means, if I want to find out the what is deflection at this node due to Pij that is somewhere here, I can be anything, j can be anything, depends on number of divisions. How will I find? I will say the pressure Pij into area, because we are taking very small areas, that means there is no need of extra integration. It will simply will be Pij into dx into dz, that is going to give me force, and this is going to give me the distance. What is the distance here? In this case, what I will do, I will subtract I minus phi square. If there is a fifth node, then it will turn out to be 5 minus 5, that will be 0. Similarly, j minus third node, that is here, the pressure is a j node, and minus where we want to evaluate. So, j minus 3 will be square root here. Now, this can clearly see when we want to find out the deflection phi 3 due because of the pressure phi 3, this will turn out to be infinity. That means, when we do computer programming, we need to avoid that. If I want to find out the deflection under phi 3, I will not find due to pressure phi 3. Whenever the pressure phi 3 number comes, I have to simply bypass that. I do not have to add, that means only maybe say 50 by 50 matrix, I had to avoid one point. Say whenever this deflection and this deflection, this node sequence and this node sequence are same, I have to avoid this summation. Remaining all other points, I had to account the summation. In the 50 into 50 except one, so the 2499 pressures, we will find out what will be deflection because of 2499 pressure at this. However, if you know the boundary condition, the pressure is 0 at the extreme boundaries, then we may avoid those points also, because we know the 0 pressure will not cause any deflection. We can avoid the calculation of boundary. We can say start from a 2, go for the 49. If the we have a node limit from 1 to 50, when 1 it will give a 0 pressure, 50 again it will give a 0 pressure. So, we will start from 2 to 49 in x direction as well as in z direction. So, that will reduce computational efforts. This is the what we are saying, that when we use this kind of a device. Now, if I already solved the pressure equation, or we already solved Reynolds equation, we already know what will be the value of Pij at every node. Of course, so we can intermediate, we can put in between also when we are going through iteration loop. However, this is what I showed, there is a Pij here. We will calculate the pressure with area, nearby area, the dx and dz, and now we are trying to find out what will be the effect of this pressure force on this point, and will be a number of points over here. Now, we continue with same, and what is the difference when we were discussing about the hydrodynamic lubrication, the whole hydrodynamic lubrication equation have been represented in terms of non-dimensional numbers, and this is a dimensional. We cannot simply combine non-dimensional with the dimensional numbers. So, what we need to do, this whole expression need to be converted to non-dimensional numbers. Now, to do that, instead of x dx square, we can use a non-dimensional number, that is a dx bar square, and there will be multiplication of maximum dimension in x direction. Similarly, for the z side also, instead of z, we will write a dz into z and a whole square of that. Similarly, here instead of dx, we are writing x and dx bar. Instead of dz, we are writing capital Z, that is the maximum value of z in z direction into dz bar. Now, we can use a relation the way we have done in hydrodynamic lubrication. We normalize x by z, we were using that bracket x by z bracket. So, I can take out this complete expression out. So, the z square dz square, take common out of this, and there is also a numerator z dz, and here it is a square root. So, z dz bar will be cancelled out, and expression will be modified something like this. You say that capital X dx bar, this is a non-dimensional, this is a dimensional. Here it will turn out to be x divided by capital Z. So, x divided by capital Z is turning out to be non-dimensional, and we do not have any other term over here, right. Now, this is why we have taken, because we know dx bar and dz bar are equal. In hydrodynamic lubrication, we took dx bar equal to dx z bar. If those are not taken equal, then we cannot take this as a common. We say that in this case we are taking both dz bar out and dx bar and dz bar both out, assuming dx bar is equal to dz bar. Otherwise, we will not be able to take out, and as we have already done in hydrodynamic lubrication mechanism, when we were solving this equation with a non-dimensional numbers or in a non-dimensional form of the Reynolds equation, we already took those assumptions. We are just repeating here. Now, this is a what? This is the whole non-dimensional number. I minus phi square, I is a number, x bar d is a non-dimensional, is not going to have any dimension, z minus 3 is only a number, it is non-dimensional. Now, what is only dimensional here? Here the Pij is a dimensional, x is a dimensional, and E is dimensional, and if we try to non-dimensionalize it, that we will get deflection in terms of non-dimensional number. We did pressure normalization in hydrodynamic lubrication using this relation. We said the P bar, that is the non-dimensional pressure, is given as P, that is a dimensional pressure, divided by 6 eta u x squared by c cube. This way we non-dimensionalize that time pressure. So, we can substitute same relation here. Instead of Pij, we can write P bar, that is a non-dimensional pressure, into 6 eta u x squared divided by c cube. When we do that, what we are getting now, this is a non-dimensional number, and this is constant coming over here. There is a 6 eta u x squared divided by c cube, and there is a capital X over here that can be transferred outside. So, whole this summation will turn out to be non-dimensional number. That will be once we know the pressure Pij, we can simply find out what will be the deflection. This is what I am trying to convey here when we are moving out, and further deflection, this is what 6 is a number, 1 minus eta square is a number, and 1 minus nu square is a number, eta is a Pascal second, u is a meter per unit second. So, second and second will be cancelled out, this will turn out to be Pascal into meter. Here there is a meter cube. So, meter cube and meter cube will be cancelled out, still we have Pascal into meter, and E is in a Pascal. So, Pascal will be cancelled out, here it will turn out to be only meter, and we are dividing by C to normalize it, so to non-dimensionalize it. So, meter divided by meter. So, whole this turn out to be non-dimensional number. Now, we have converted whole dimensional deflection in non-dimensional deflection. So, this equation can be simply used in film thickness expression. Wherever the film thickness we have calculated, we can add this expression, we can find out film thickness distribution over a x direction as well as a z direction. Now, we need a slight modification in a finite difference method, which we have done in hydrodynamic lubrication. If you remember what we did, we converted finite difference method, we use a finite difference method as central difference method, and we evaluated h at the half node. Now, when we calculate h at the half node, deflection cannot be added. In that case, again we have to calculate a deflection of the half node, which is slightly more cumbersome. That is why we are trying to change this expression, so that we do not require any half node calculation. We can go ahead the full node calculation. What is the meaning of that? Let us start with this first term. There is a pressure distribution in x direction, which depends on the film thickness and the pressure. And what we are doing, we are going with the parts. first we are taking differentiation of h, that will turn out to be 3 h square dh by dx bar into dp bar by dx bar. So, first term will be that, second term will be h bar cube out, and this will be second differentiation of pressure. So, we will be having two terms and we need to do a central difference for the two terms. Now, you can see the first one, when we are first only integrating first h, that is a 3 h square, 3 h bar square, that is comes over here, into dh bar dx bar, which is shown over here, h bar I plus 1 j minus I minus 1 j. This is what a central difference of film thickness gradient. This is the second term into not second term, is a multiplication factor dp by dx, that is can be evaluated here, something like a p bar I plus 1 j, p bar I minus 1 j divided by 2 x. So, this is going to be complete the first term. Second, h cube h bar cube is common, that is shown over here, and after that is the second derivative of the pressure, that can be simply given as p bar I plus 1 plus p bar I minus 1 minus 2 p bar I j and divide by del x square. So, this is for first expression in x direction, same thing for the z direction. The same thing, we have just change only I and replace I with a j and j and with I. You can see here 3 h I j square is the same. Here is a h I plus 1 j, instead of that here we are writing I j plus 1. Again somewhere here this is I minus 1 j, what we are writing here is a I bar j minus 1. That means, we are taking a variation along the z direction. In previous case, we assume that there is no variation in film thickness along the z direction, variation was only in along the x direction. But however, when we are calculating the pressure, and pressure is deforming the surface, and that will deform also in the z direction, is nothing like that we need to avoid, we need to account that also. So, this is given over here, same later is the same term, and this will remain same, is not a much variation, the way we have done in hydrodynamic lubrication, same thing. Now, substitute, we get pretty lengthy equation, this is very big equation, too many terms, but we have to bear it. We do not have an escape route for that if we want to get a solution from for this kind of expression. What is being done, terms have been separated. You can see p I plus 1 j term, p I minus 1 j term, p I j term, p I j plus 1 term, p I j minus 1 term. They have been separated out, and in bracket we are writing in terms of only the complete node, it is not a half node. The way we have done in hydrodynamic lubrication, that was a half node, while in this case we are writing complete terms. Complete node is a I plus 1, I minus 1, I j, and similarly j plus 1, j minus 1, there is no half term. An interesting thing is that after rearranging, we are getting much lesser number of cubic terms. Cubic term is coming only in h I j, we do not have any other cubic term. So, number of calculation will be reduced with this kind of formulation. The only problem with this kind of formulation is that it is involving more number of terms compared to the terms which we seen in hydrodynamic lubrication mechanism when we use a finite difference method in hydrodynamic lubrication. Now, this can be rearranged because at any time we need to find out what will be p I j for given value of p I plus 1, p I minus 1, p I j plus 1, p I j minus 1, and the source term. This is source term. That is why we need to rearrange equation in a such a manner we can find out p I j. That is that can be arranged something like this. So, now we had a smaller equation, now it is turning out a much bigger equation, right. So, because we have divided this one also 2 h I j and 1 plus x square by z square or everywhere. We have divided here, we have divided here, that is why the number of terms are increasing, and this expression is turning out to be slightly lengthy, but when we do computer programming it is not going to be much lengthier compared to earlier expression what we have done. We are going to get a good results without much problem. Now, first point after doing this kind of derivation, First point will be that let us compare with this formulation and previous formulation without accounting elastic deformation. In this case, we have not added anywhere of elastic deformation for time being. Only thing what we have mentioned that film thickness will change. Under deformation, there will be more separation, film thickness will increase, that need to be accounted. But yet we have not accounted here anywhere the delta is 0, it should give me the same result as the hydrodynamic lubrication mechanism. If it is not giving the same result, that means I have made some mistake in derivation, I need to verify it again. However, what I am trying to convey is something like this. Here HI at any point will be given as a H hydrodynamic Ij, that means, so whatever the film thickness was calculated for hydrodynamic lubrication plus whatever the deformation is happening, and that will be also deformation at the Ij. At every node deformation will be calculated and will be added in this case. So, this will turn out to be more complex, much more time consuming compared to the hydrodynamic lubrication, but still there is a point we can verify this whole formulation keeping elastic deformation as a 0. Using this coding, maybe add with elastic deformation, make a complete code, and after that use put everywhere elastic deformation is 0. Then we can compare this new formulation which we have done with full node without accounting half node with earlier program which we have done with a half node. Now, that this slide is going to show the comparison, is there any change. This is done with half node calculation when we are counting pressure distribution and the viscosity effect of the viscosity on the pressure due to pressure or with the viscosity thickening. The first term viscosity thickening is not accounted, while in second figure viscosity thickening is counted. Now, with this is with the previous formulation and the half node formulation. Now, this is with a complete formulation without accounting half node, we are using only the full node. I am not able to see any difference over here. This is without viscosity thickening, this is also without viscosity thickening. This is by using the using the expression for the half node, this is using full node. So, that means we have not made any mistake in our formulation. Results are almost same, not a single percent, not a 0.1%, not a 0.01% change in the results. Same thing with this also, we are saying here the 4 point something, we say around the 40 bar pressure, or we say that 40 megapascal pressure here, and same thing over here. Okay. So, we are not finding any difference in this curve and this curve. We here in this case we have not counted viscosity thickening effect, while in this case viscosity thickening effect have been accounted, and we are not able to find any difference in these results. That means, what is the formulation, whatever we have done in previous slides, that is all right, it is not going to change the results, it is not affecting the results. Now, the time has come to find out what will be the elastic deformation. So, this is elastic deformation. What is being done over here? We calculated the pressure at every node and simply found what is the deformation without going with iteration loop, without accounting in the film thickness expression. This has been done only once we know the pressure, find out the deflection at every node, and we know the 50 by 15 node. At the initial there will be 0 deflection because the pressure is 0, after that is going high and it reaches to some value maximum. Now, if I compare with the non-dimensional film thickness, we had roughly a 20 by 30 micron, number 2 by 3, the 0.66 value at the exit, and the entrance it was a 4 by 3, it was 1.33. Now, what we are saying here, in that film thickness this will be added. So, whatever the 2 by 3, in that case the film thickness this expression, because this is going to add because of deformation, two surfaces are going to get more separation due to deformation, and you count this kind of film thickness variation. Now, what will happen if I increase the film thickness at any point? Pressure is going to go down, pressure will decrease, and we require really iterative loop to come up with the final results. What I am trying to say? Use hydrodynamic lubrication mechanism, use that algorithm, find out the pressure at every node. From those pressure, find out the deformation at every node, redo it now. You can come back, calculate the film thickness at every node, use those film thickness expression to find out hydrodynamic pressure. From hydrodynamic pressure, again find out what will be deflection, and it need to go through a number of iterations to find out the final convergence solution. Or what we are saying, initially assuming elastic deformation 0. After that, we know what will be the hydrodynamic lubrication film thickness, and using this expression we find the pressure. After finding the pressure, we find this elastic deformation. We go back and change the film thickness expression, and again redo it. Again find out the hydrodynamic pressure. From hydrodynamic pressure, again you find out the delta. From delta, again come back to this equation, find out the film thickness. A couple of iteration, not couple of iteration, maybe say 100 iteration plus, it may give some solution, and that is given over here. When we are not accounting iterations, we are not accounting in a change in the geometry, and after that we evaluating the pressure, and here we are going through number of iteration, and this is the final curve. What we are able to see here, the deformation after a number of iteration is again reduced. That is clearly the pressure will come down, reduction in pressure will reduce the deflection, and that is why the overall deformation will turn out to be lesser. You can see here it is crossing the 4, it is reaching maybe say 5.2 or something like that, 0.052, while here it is a much lesser than that, even the 0.038. So, there is a variation. What this means that we need to account this variation in film thickness, so that we can find our right results, otherwise it will be problematic. Now, if we account the pressure distribution with elastic deformation, accounting elastic deformation, what we are going to get is something, this pressure distribution something like this, shows a 3 point something as the pressure, and if we do not account pressure elastic deformation, use only the pressure viscosity relation, do not account the pressure deformation of the surfaces, we are going to get much different results. You can see here, when we are not accounting elastic deformation, pressure shown over here is something more than 4. When we are accounting pressure deflection due to pressure, the pressure has come down. Or in other word, we need to account this kind of elastic deformation, or we need to go through elastohydromal lubrication to find out the right results, the right pressure distribution, because the pressure distribution is the first point to find out the friction losses also. If we do not account pressure, the right pressure distribution, the friction losses will be different, mass flow rate will be different, and most of the parameters which are dependent on the pressure will turn out to be different. It will not give accurate results. So, as far as possible, if the pressure is high and this is going to affect the elastic deformation, or is going to deform the elastically that surface, we need to account. What we say, due to elastic deformation, maximum value of pressure decreases and more uniform pressure distribution occurs. What is the meaning of that? You can see there is this stretch is much larger than this stretch, or there is a more uniform distribution. That means load carrying capacity is not going to decrease. Load carrying capacity of these surfaces will remain same. Only thing, the maximum pressure is going to decrease, and most surfaces is going to sustain same pressure. Or in other words, if I say this is a without elastic deformation, if I account elastic deformation, pressure distribution will change something like this. However, area under this curve is not going to change. That is why the load carrying capacity of this will remain same. Only what is happening, the maximum peak pressure, the peak pressure here is different than peak pressure over here. Our pressure is going to decrease in this case. So, this is the recommended case. We say the elastic deformation of the surfaces need to be accounted properly. If we do not account, we may not get good results. So, we will continue with full film lubrication mechanism. We will be considering energy equation, because we have considered yet only elementary treatment of thermal heating, while we are going to consider now in a slightly deeper, more description will be given in next lecture. So, most of the next lecture will be more focused on the energy equation, how we are going to account the temperature difference, how we are going to evaluate the temperature difference, and how that temperature difference is going to change the load carrying capacity. Thank you.